So what we do here is we identify molecules and especially precise molecular structures. And so what we have here, funded by our roadmap subsidies, is a new mass spectrometer. And that mass spectrometer tells you exactly the molecular weight of a molecule, and that's exactly the sum of all the atomic weights in a molecule, but it does not tell you so much about how these atoms are connected together. And that's why we combine it with FELIX, the infrared light of FELIX, so that we can do infrared spectroscopy inside our mass spectrometer. From that infrared spectrum, we derive exactly the molecular structure of species like this, but also actually of biologically relevant molecules, and especially also what we call biomarkers. These are molecules that exist in your body and that tell you something about the state, but also, for instance, about the disease state of a patient. If a patient has a certain disease or not, can be derived from the presence of certain very specific molecules in the body. That's exactly what the doctors and medical people need in order to be able to connect that molecule to a particular disease, so to a particular metabolic route that occurs in the, in your metabolism, and that is then somewhere disturbed, and that leads to the accumulation of one particular molecule with one particular structure, and that needs to be identified exactly to make that diagnosis. We have published now one biomarker, the structure of one biomarker. That's a biomarker for a specific metabolic disease that has been identified, and that biomarker can be used now for early diagnosis. That's done already in newborns, so it's been entered into the heel prick, so the newborn screening program, actually at Radboud here. So we can. These are rare diseases, but they are not very nice diseases. So if you diagnose them early, you give really a better life to these patients.
Does that also mean something for the research of disease itself?
Absolutely, because these are new molecular structures that we identify and accumulate in these patients. And so what are the biochemical consequences of higher concentrations of these molecules it tells you maybe also a way to not to cure but to treat these diseases in these patients. You can try to remove these molecules in some biochemical fashion, for instance, or to lower their concentrations. We have a number of biomarkers sort of in the pipeline towards identification for a number of different of these metabolic diseases. So we do this in collaboration with the Translational Metabolic Laboratory here at Radboud UMC. And they constantly find new biomarkers or unidentified molecules in the samples of these patients, and some they can identify with their own methods and some not, and then they bring them to us. So when we identify a molecule, we do that sort of reference-free in the first instance, so we have no reference because these molecules often have never been synthesized before. And we do an identification based on a predicted infrared spectrum, and if we have a very good prediction, then we actually go to Floris Rutjes and ask them, can you synthesize exactly this molecule? And when we have that physical standard in hand, then we can do a definite identification, because then it's not only the mass spectrum, but it's the infrared spectrum, it's retention time, it's everything should match. I think this is not only applicable in medical research and biomarkers, but everywhere where you apply mass spectrometry to analyze complex mixtures. And there are many problems in environmental chemistry, forensic chemistry, food chemistry that you can think of. You always encounter in your mass spectrum peaks that you are not able to identify, and I think that this is a good method to use in all of these to all of these problems.